Now in the second part we will prove two laws of the iterated logarithm. So first we'll prove the law of the iterated logarithm for the Brownian motion, which is the following result. Okay, it says that when you take an upper limit when time goes to plus infinity of the Brownian motion at time t scaled by the square root of 2t times this iterated logarithm. So it's the natural log of the log of t. Then this lim sup is equal to 1 with probability 1. And then in our next result, we will use the Skorohod's embedding theorem to transfer this previous theorem for the Brownian motion to random walks. Okay, namely, if we have this sequence of IID random variables such that their expectations are 0 and the second moment is finite, and as usual we'll denote by Sn the sum of the first 10 of them, okay, then we'll show that the upper limit when n goes to infinity of the sum scaled by square root of 2n iterated logarithm of n is also 1 almost surely. Okay, and from now on we will often use the following shorthand notation. Okay, instead of writing this iterated logarithm or even this whole expression in the denominator, we'll just write u of t as the square root of 2t log of t. Okay, and then we'll start with the following technical result that will actually be used in the proof of both of the above theorems. Okay, namely we'll prove the following lemma, which states that if we take some epsilon, some positive epsilon, now we'll use it when epsilon is small, so let's say when epsilon is between 0 and 1, then the upper limit when time s goes to infinity of the supremum of the increments of the Brownian motion wt minus ws is scaled by this function defined above at time s. Okay, and this supremum is taken over the interval of t between s and 1 plus epsilon times s. So in other words, as this s gets very large and we consider the interval which is relatively small compared to s, then the increment of the process on that small interval uniformly when scaled by this function can be controlled by something small. So in particular we'll prove that this can be bounded by 8 square root of epsilon almost surely. So this lim sup with probability 1 is bounded by the small constant. Now in the proof of this result we will first consider this times s going to infinity along some geometric sequence. So we'll take some positive epsilon and we'll take a sequence of times tk of the form 1 plus epsilon to the k. Okay, and then let's also denote by mk the square root of 2 epsilon times this function u above evaluated at time tk. And let's see how we can control the probability that the supremum over the interval between tk and tk plus 1 of the increment of the Brownian motion between times t and tk is greater or equal than this threshold mk. In a second it will become clear why we choose this particular threshold and where this function u appears from. First of all, by the stationarity of the Brownian motion, of course we can consider the interval from 0 to tk plus 1 minus tk and just look at the Brownian motion at time t. Now the fact that with absolute value we exceed level mk means that we either exceed level plus mk or minus mk, and so by symmetry we'll just bound this by twice the probability that the supremum over this interval of the Brownian motion without the absolute value is greater or equal than mk. And here we recognize that we computed this probability of the supremum in the previous section using reflection principle, and in particular this was equal twice the probability at the end point. So in other words, here we have 4 times the probability that this Brownian motion at time tk plus 1 minus tk exceeds this level mk. Now if we scale both sides by the square root of this time increment, on the left hand side we get standard Gaussian random variable, so we have a good control for the probability of this tail. Okay, namely, this will be bounded just by the exponential to the minus 1/2 times this constant squared. So mk squared divided by tk plus 1 minus tk. Right, but if we look at the definition of these constants above, we get that mk squared will be just 2 epsilon times u at time tk, and let me now recall that u was 2k, or u squared was 2k log of tk, and also in the denominator the increment, because this is a geometric sequence, it will be just epsilon times tk. And so here we can cancel epsilon and tk and cancel 1, 2, and we see that this becomes 4. Now e to the log will give us 1 over the log of tk, and then we have square left. Okay, and again, because we chose tk to be geometric, so this is log of tk is k times log of 1 plus epsilon to the power 2. Okay, so in particular, you see in this calculation, this threshold mk was chosen in such a way that we get a convergent series, right? That the sum over k here of this will be bounded, so we can apply the Borel-Cantelli lemma. Right? So by Borel-Cantelli lemma, we know that for large enough k, of course, large enough, it depends on the point omega in your probability space, but since these events cannot happen infinitely often, means that for large enough k, whenever your time t is on this interval between tk and tk plus 1, we will have control of the increment by square root of 2 epsilon times u of tk. And this is already pretty close to what we want. We want to have a control over the interval of this form, but for all s rather than over the geometric sequence. And now we just reduce that the case of the general time s to this geometric sequence. In particular, if we want to look at the interval of time t between some s and 1 plus epsilon s, let's just find which interval in this geometric sequence our time s falls into. So let's say it falls into this interval corresponding to some index k. Then these two conditions together, of course, imply that tk is less than or equal than s, less than or equal than t, and at most tk can be tk plus 2. So we have this relationship between all these times. And so if we look at all these different times, so tk here, tk plus 1, tk plus 2, and then we have some times s, and time t could be on the first interval or on the second interval, but for certainty let me put this on the second interval here. Right? And we want to control in the lemma the increment between these two times, right? And instead we'll write this increment as a linear combination of this increment, and this increment here. And if you write it as a linear combination, then just by triangle inequality you can bound the increment by those three increments where the starting point is in this geometric sequence. But for large k, we already have a good control of those increments above, and so you see here that we have two such increments on the first interval, which are controlled by square root of 2 epsilon u at time tk, and we have one on the second interval at most, so that will be bounded by square root of 2 epsilon u at tk. And then you can easily check that since here we are looking in the limit when s go to infinity or k go to infinity, for large k you can bound this by 8 square root of epsilon u of tk. Okay, this is just a simple calculation. I'm going to omit it, and so finally we can replace tk by something bigger, by s, and we get the control that we want. Okay, so with probability 1, when s goes to infinity, we have this uniform control for all t on this interval between s and 1 plus epsilon s. Okay, so that finishes the proof of this technical lemma. And so using this lemma, we can now prove the law of the iterated logarithm, first for the Brownian motion. Now the proof of this is divided into two parts. In the first part, we prove inequality in one direction, namely that this upper limit scaled by this function u of t is less than or equal than 1 almost surely. And in the second part, we show that this is greater or equal than 1 almost surely. Now both proofs are very similar in some sense. This first one is slightly more involved, and so I will consider only the first one, and I will leave the second part to the notes. This first inequality is actually where we use the lemma that we just proved. Okay, but we begin the proof by again considering some geometric sequence of the form some constant a to the k for a greater than 1. Just like in the previous lemma, in a second we'll take this a to be of the form 1 plus epsilon, but here I'll first write something a little bit more general, because that's how it's used in the second part as well. Okay, and then we want to see how we can control the probability that along this geometric sequence the Brownian motion slightly exceeds this level ut. So it's greater or equal than 1 plus epsilon times utk. Right? And we want to show that this cannot happen for infinitely many k, because the lim sup should be actually less than or equal than 1. So we cannot exceed 1 plus epsilon level infinitely often. And again, since we are going to use Borel-Cantelli lemma, this will explain the appearance of this function u. Now in the first step, of course, we reduce to the standard Gaussian just by scaling by square root of the time, both sides. And you can see that when you scale the function u by square root of the time, what you are left with is just square root of twice iterated logarithm of that time tk. Then for the tail of the Gaussian, in this part we can just use the upper bound as we did before, but let's notice that we actually know the asymptotic behavior of the Gaussian tail precisely. We know that this is 1 over square root of 2 pi, 1 over the time, where the time here is, or the tail here is this 1 plus epsilon square root of 2 log tk. Right, and the equivalence here in the sense that the ratio goes to 1 as k goes to infinity. K times the e to the minus 1/2 this tail squared, so 1 plus epsilon squared twice log tk. Right, and then if we write this in terms of explicit definition above, in other words, we replace tk by a to the k, we can see that the exponential here becomes 1 over k log a to the power 1 plus epsilon squared. And again, this is summable series, and so that explains the choice of this threshold uk. And so by Borel-Cantelli lemma, we know here that along this geometric subsequence, these events cannot happen infinitely often, so the Brownian motion has to be bounded by 1 plus epsilon times this function u of tk for large enough k, where again large enough depends on the point omega in your probability space. And then to control the Brownian motion for arbitrary time t, well, when you take a time t, let's consider a particular interval that it falls into. So along this geometric sequence tk, let's say it's in between tk and tk plus 1. And now let's actually take a to be, like in the previous lemma, to be also 1 plus epsilon, right? So tk will be 1 plus epsilon to the k. And we want to control the ratio of the Brownian motion and ut, and now we just have to relate this to this geometric sequence. So we'll simply add and subtract w of tk, and also write 1 over u at time t as 1 over u at time tk times u at times tk over u of t. So in other words, we multiply and divide by u of tk, and then we also have this increment at time t and tk, and the same the same factors as before. Well, for large k, for the first ratio, we know that for large enough k, this will be eventually bounded by 1 plus epsilon, right? And also tk is less than t, so the second ratio is bounded by 1. And then by the previous lemma, we know that this increment for large k again, so if you look at the previous lemma with s given by this tk when s goes to infinity, or in other words when k goes to infinity, this expression in absolute value is controlled by 8 over square root of epsilon in the limit, right, when you take a limit. So in particular, this implies that the lim sup, when t goes to infinity, from what we proved before, for the geometric sequence you get something bounded by 1 plus epsilon, and for the second term by previous lemma, this is bounded by 8 square root of epsilon. Okay, and so what remains is, so this happens with probability 1 for any epsilon, and now you just make this statement for some sequence of epsilon that goes to 0, and so you get the result that we want, that this lim sup is less than or equal than 1. So this finishes the proof of this inequality in one direction, and as I said, in the other direction it's pretty much the same calculation. It's in some sense is easier because you do not need to use the previous lemma. Okay, you just need to use the calculation like we did here just for the increments, because we want to use the Borel-Cantelli lemma in the other direction. So we want the events to be independent, and that is achieved by looking at the increments of this Brownian motion. Okay, but since the calculation is almost identical, I will not repeat it here and just refer to the notes. Given this law of the iterated logarithm for the Brownian motion, we now want to see how we can derive from it the law of the iterated logarithm for this IID sequence. And this is where we will use the Skorohod's embedding that we proved in the first part, right? To show that the lim sup when n goes to infinity of the sums divided by the square root of 2n log n is also 1 almost surely, as long as our random variables that we sum are centered and have finite second moment, and they are IID. And so by Skorohod's embedding, we can find a stopping time, let's say tau 1, such that the Brownian motion at that time is equal in distribution to any element in this sequence, let's say y1. Okay, so stopping time tau 1 is such that w at time tau 1 is equal in distribution to y1. Now, in addition to Skorohod's embedding, again we will appeal to the strong Markov property, namely that the increment of the process after this time is independent of the sigma algebra up to that time, and moreover it's equal in distribution to a Brownian motion. And then with this information, then we define stopping time tau 2 for this increment process. So for this increment process, we consider a stopping time tau 2 such that this increment process at that stopping time is equal in distribution again to y1, but let's just say here y2. And because both this stopping time and this increment here are defined in terms of this increment process, we know that they are independent of the sigma algebra up to stopping time tau 1. And this stopping time tau 2 was defined by exactly the same procedure that tau 1. So in particular, we know that they are just independent copies of each other. So tau 1 and tau 2, they are independent and identically distributed. Right? And the increment we wrote here is independent of the process W at time 1. So indeed, as a pair, you can view those as equal in distribution to y1 and y2 because they are also independent and identically distributed. Right? So W tau 1 and the increment, okay, they are also independent and have the distribution, the same distribution as that sequence y1, y2, and so on. Okay, and then we just repeat this recursively. Okay, and so recursively proceeding in the same spirit by considering the future increment process which is independent of the sigma algebra up to the stopping time, we can define this IID sequence tau 1, tau n, and so on, such that if we denote by Tn the sum of the first 10 of them, the increment, so the increment of up to the next stopping time, of course it was Wtn minus Wtn minus 1. This sequence of increments will be IID, and it will be equal in distribution to our IID sequence yn. Moreover, let's note that when we appeal to the Skorohod's embedding theorem, the stopping time that we constructed, it had a finite expectation. Okay, so that was part of the Skorohod's embedding theorem, and in particular, its expectation was the expectation of the process at that time squared, and since this is equal in distribution to y1, this expectation is 1. So expectation of all these tau i's is equal to 1. Okay, and then given this information, now we want to control the upper limit of Sn divided by un. Okay, and instead, of course, we will consider now the copy of this sequence written in terms of the Brownian motion. In other words, the sum up to time n is replaced by W at time Tn and scaled by Un. Okay, so we are going to add and subtract w at time n. So this can be written as w at time n over Un, something that we already controlled in the law of the iterated logarithm for the Brownian motion, right, plus this increment divided by Un. Okay, so for the first term, we already know that if you take a lim sup when n goes to infinity, this will go to 1 by the corresponding result for the Brownian motion. But in the second term, we just noticed that by the strong law of large numbers, this Tn divided by n, right, it's just the average of IID random variables tau I. And so by the strong law of large numbers, this converges almost surely to the expectation of tau 1, which we just said it's equal to 1. So actually, this random time Tn is relatively close to n. So in particular, because this is the almost sure convergence, if you take any epsilon, you know that this time Tn will be between n divided by something slightly bigger than 1 and n multiplied by something slightly bigger than 1. Okay, and so in the limit, when n goes to infinity, or let's say for large enough n, you have this relationship. In particular, if you take this to be an S in the lemma that we proved above, then this right-hand side will be S times 1 over epsilon, right? So our time here is on the interval between S and S times 1 plus epsilon. And so when S is going to infinity, so here when n is going to infinity, with probability 1, we have a good control of these increments, right? So if we recall, we proved that the lim sup when s goes to infinity, so here I'll replace that by n, when n goes to infinity, of wtn minus wn in absolute value divided by u of n. Well, we have to compare both tn and n to this s, which is slightly less than n. So in particular, n is also in between. And so as a result, this will be bounded by twice times the control that we had in that lemma, which was 8 square root of epsilon. But again, because this lim sup is controlled by the 16 square root of epsilon for any epsilon, that actually means that this lim sup is equal to 0 almost surely, right? Just by letting epsilon go to 0 along some subsequence. So if we go back and look at this decomposition here that we started with and take the lim sup on both sides, right, we know that the first term goes to 1 by the law of the iterated logarithm for the Brownian motion, and the second term goes to 0 because of the strong law of large numbers, right? Because of the fact that Tn is very close to n, and combined with the control in the above lemma. So as a result, we conclude that the lim sup of wtn over un is equal to 1 almost surely when n goes to infinity. And in one of the earlier chapters, we had an exercise which showed that if your sequence has the same distribution, that this type of statements about almost sure convergence, they hold no matter on which probability space the sequence is defined. So here we have a particular realization of our sequence in terms of the Brownian motion, but of course this statement by that exercise implies that the same statement holds for any sequence on any probability space as long as it has the same distributions. Okay, and so as a result, this finishes the proof of this strong law of large numbers for sums of IIDs. Okay, and let me also mention that in the notes we also state the so-called local law of the iterated logarithm for the Brownian motion. And as I mentioned before in the exercises, using the Skorohod's embedding theorem, one can give an alternative proof of the Donskir's theorem about convergence of the rescaled random walk to a Brownian motion. And so this wraps up this section and the chapter on the Brownian motion.